It's a pleasure to speak with everyone today. As she mentioned, I'll be talking a bit about searching for new physics with low energy techniques. So what exactly does that mean? What do we do in our laboratory? Well, the way that this breaks down is essentially into two categories. We look for rare events, so events, different types of decay processes or interactions that have never been seen before or have really only been seen a very few times. And we look for new particles. And in looking for new particles, what we're often focusing on is looking for something that could constitute the nature of the invisible mass that doesn't seem to interact with light and doesn't seem to interact with the rest of the matter that we're used to looking at in the universe. Now, there's a lot involved in both of these and there is some overlap, but for today, what I plan to focus on is sort of this rare search. I'm happy to answer questions about the new particles part, but it's interesting to note that when we're looking for these rare events, we can often use many of the same techniques to search for the new particles, in addition to using alternative techniques. So when we talk about being at the intersection of a bunch of disciplines with a sort of a description like nuclear particle, astro, what are we actually saying? Well, when we're looking for these new particles, a lot of times what we have to do is combine what we know about the really, really small with what we know about the really, really large. And we kind of pick out these four because they encapsulate the types of descriptions that we're using when we're trying to make those connections. So just as a quick note for people who may not be as used to what the distinctions between these are, or might not have heard of them, when I speak of particle physics, what I'm speaking of are elementary particles and their interactions. And we'll talk a little bit more about this in a moment, but these are the things that make up the things that make up atoms. When I speak of nuclear physics, we're looking at taking a little bit of a step back. We're actually looking at how the nucleus of an atom behaves and interacts with other matter. Now, if we take a huge step back and look on much larger scales, we can think about astrophysics. And with this, what we're doing is we're using physics, chemistry, and many other disciplines to study astronomical objects and events. And when we are talking about cosmology, what we're doing is we're basically taking the combination of these things and trying to understand what it means for how the universe began, how it's developed into what we see now, and what we expect things to look like in the future. And so trying to understand how things work on the very smallest scales often has impact on what things look like at the beginning of the universe when we expect it was really, really small and really, really dense and compact. On the same note, looking at how the universe looks today can give us some understanding and insight about how we expect large numbers of these particles to have behaved. And we can use it to draw some conclusions, one for the other. Now, on the particle physics side of things, we typically organize the way that we think about it with a structure that we call the standard model of particle physics. Now, the standard model, if you can see the sort of background of this slide, is actually sort of a huge equation. What you see is really only sort of like the middle snapshot of it. But what it does is it describes the elementary particles and their interactions with themselves and with each other. And so typically these get grouped into a few categories. On the upper left, what you see, so you see U, C, T, D, S, B, these are the quarks, and these are the subatomic particles that essentially make up the nucleons, so the things that make up the nucleus of an atom, protons and neutrons. Below those, you see E, mu, and tau, and nu, these different kinds of gray ones at the bottom, so nu E, nu mu, nu tau. These are called leptons, and these are particles such as the electron, which is the lightest one that you see here, that behave a little bit differently. They don't respond to all of the same forces that the quarks respond to. The neutrinos here are really, really light particles that actually don't have any electromagnetic charge. And so they also behave kind of interestingly. And as it turns out, there are a lot of things that we don't actually understand about them and that don't actually get included in the standard model. So the neutrinos will turn up again in a few slides. So keep an eye out for those. So another category is sort of standalone here. You see this particle, the Higgs boson, which many may recall several years back. In fact, this is about the 10th anniversary of, a little beyond that, of the discovery of the Higgs boson. And what happens with the Higgs is that other particles tend to interact with the Higgs boson, and that is what gives these other particles mass. So it kind of, by them interacting with the Higgs, it kind of makes it a little bit more difficult, in a sense, for them to respond, let's say, to interactions or forces from other particles. And then on this last side, what you actually see are what we call sort of force-carrying particles. And so these include the W and Z bosons, the photon, which is the one that's marked by a gamma on the left, and then you have these gluons, this sort of multicolored thing that's on the right. Now, the forces that these mediate are shown with these three pictures on the side here. So this top one represents the strong nuclear force, and this is what holds these subatomic particles together in the nucleons that make up the nucleus. On the bottom here, we have the weak nuclear force, or we have an image that sort of represents, I should say, the weak nuclear force. And these are, the force there is sort of mediated by, mostly by the W and Z bosons, in addition to having some electromagnetic contributions. And the weak nuclear force also plays a role in the way that nuclei decay. And that will also come up again. And then in the middle here, you see this brilliant strike of lightning, and this is representative of the electromagnetic force. Electricity and magnetism are really two sides of the same coin. And all of these forces are actually tied together. The particle that really mediates or facilitates the interaction of the electromagnetic force is the photon. And so taken together, this is essentially the picture that we get when we're talking about the standard model of particle physics. So that's sort of like how we think about and organize on the really small scale in our minds. There is also a picture of how one may think about cosmology and how essentially how the universe has developed to the point that it is now, and what we expect for things to have, the different stages we expect things to have gone through, and what we see today. So this model is often called the concordance model, perhaps in some cases. And what you see here in this illustration is essentially a picture of how things progressed from the left-hand side, where we had this really hot, really small, really dense singularity, this event that happened at every point in space, where suddenly you now have a bunch of energy that's expanding into the universe. There's inflation, which people are studying to kind of understand how this happened. What we'll focus on is the sort of particle era and moving out to today. So you see that it goes through these different stages. So first you have the possible forming of these dark matter relics. And so this invisible mass component, we think, was made out of particles that we just don't really interact with very strongly. But in the early universe, when everything was hot and close together, the interactions were much more obvious and much stronger. But as everything sort of spreads out and cools down, then you have the opportunity for nucleons to form. So you start having things relaxed enough for protons and neutrons to sort of form and then come together. Eventually, things spread out enough so that you have nuclei form, so that the neutrons and protons are able to combine into these nuclei that eventually form atoms. At some point, things spread out and cool down enough that those atoms, which are going to have an electromagnetic charge, are going to be able to attract the negatively charged electrons, and which will form clouds around them. And that essentially neutralizes the atom and allows for the photon to be able to just kind of stream freely without being always caught and bounced around by some of these charged particles. So at this point, you now have this sort of light that's able to go an appreciable distance. And this is what we really refer to, in a sense, as the cosmic microwave background, or when this radiation becomes visible. So what I'm referring to is sort of the surface of last scattering. So now the universe has sort of become a little bit more transparent. And then as things continue to spread out and cool down, you have the beginning of, again, gravity is sort of pulling things together at this point, and you have the formation of much larger structures. And then things kind of progress into today, where you look out in the night sky and you see galaxies and clusters and nebulae. Along this time, you sort of have different eras when different forces were really strong, or were more noticeable than others. I'm trying to be a little bit more careful about the way I say that. But what you can also see in this picture is sort of an analog of what energy regimes would have corresponded to each one of these stages, and sort of how they might match up to the different experiments that we do to try to reproduce conditions similar to those energy regimes today. And so, for example, you have Rick in the LHC, where you are colliding like heavy ions, and so that would have been closer to the stage of when nucleons formed. And then at the LHC, when we're smashing together two protons and getting out these really high energies, and then watching kind of what forms out of that, that's closer to what things would have been like in the earlier universe. And so this standard model of cosmology allows us to organize our thoughts with respect to how we got from sort of this really hot, really dense soup of everything to the varied structures that we see from the night sky, but then also to just the world that we live in, where atoms now make molecules. When they combine, molecules are the basis of substances ranging from, water with H2O to cellulose and oxygen, et cetera, with the trees. I'm looking at some trees outside of my window. And so this is sort of our attempt to combine all of these things together into a coherent picture. Now, that being said, is there a theory of everything? Perhaps we're trying. This is part of why we are trying to sort of organize our understanding of how things work across these huge energy scales. But one thing that we do know is that this theory of everything just isn't the standard model. And there are several reasons for why this is the case. So the standard model does a great job of describing the known fundamental matter particles and the forces by which they interact. And it gives us a really consistent framework for most of these particle interactions. It also provides us with a description that brings together the equations and really unifies the electromagnetic force with the weak nuclear force, and even provides a robust description of how particles interact with the strong nuclear force as well. And so it sort of ties together the things that we saw and discussed in the previous slide. But there are some issues. One is a lot of these particles are really, really light and much lighter than other particles that are shown in the slide. And the question could naturally be why? What sets the mass scales for these particles, et cetera? Another question related to this is sort of the hierarchy problem. So there's questions of mass, and you can also think of this in terms of why are some of the forces so much stronger than others? We talked about the electromagnetic and the weak nuclear force and the strong nuclear force, but the electromagnetic force is actually not as strong as the other two, but it acts over much longer scales. Whereas the weak and strong nuclear forces are very strong, and they bind these nuclei and these nucleons together, but they really only act over short distances. And so what sort of sets the relative magnitudes of these forces and why? Skipping down for a moment, you'll notice that when I talked about the forces, I only mentioned those three. We all are very familiar with the fourth fundamental force, gravity, but that's not described by the standard model at all. And so if we're trying to have a theory of everything, in which many people are working to develop and trying to figure out ways to incorporate gravity in our model, then that is really one of the benchmarks for what you need in order to have this sort of overarching, fully encompassing theory. There are other problems as well about things like the rules and the patterns that different particles follow. Why do they keep the rules in some cases, and why do they break them in others? This has been a really powerful technique for discovering new particles and for understanding how things behave. But there are several instances that just don't seem to match up with what we expect, and that's something else that we're looking into. Another question is, why is there more matter than antimatter in the universe? This is the one that we'll be focusing a little bit on today, but just to sort of give you a preview, one of the symmetries that we see is that matter and antimatter need to be created in equal amounts. If that was true in the early universe, really they could have recombined together and everything would have sort of annihilated and we would just be a bunch of energy. So we would not expect everything that we see when we look around to be comprised of matter particles. And then, of course, it's still missing a lot of things. So we didn't really talk about dark energy, but that's also part of the standard model of cosmology. And we only touched a little bit on dark matter. And I pointed out that we really don't know what that is, and it's not included in the list of particles that we just discussed. And so if we really want to have something that's a theory of everything, then these problems also need to be addressed. So what we'll focus on today is really this searching for matter-antimatter asymmetry. And the way that we're looking for this is with a process that we call neutrinoless double beta decay. And so we'll explain this a bit in just a moment. Now, before we do, just want to go back to the standard model for a moment. So I described in detail, so the groups of particles that we have and the forces that they interact. This is another way that people sometimes sort of organize the chart so that we can see what we're dealing with. And what you'll see here is that this is about 17 or 18 particles. Some of them are included in the same block, so that's the nebulous. But what I want to point out is that these are all actually matter particles. But one of the symmetries or interesting things is that every matter particle actually has a counterpart where it has the same mass, it has the same properties that define it as being, a fermion or a lepton or a quark. But what you do is you change the electromagnetic charge. And when you flip that charge, then you have the antiparticle counterpart. So you have an up quark, then you're going to have an anti-up quark. The up has let's say a charge of 2/3. The anti-up is going to have a charge of -2/3. Similarly, for the electrons, let's say, electron has a charge of -1. An anti-electron, which we also know as a positron, has a charge of +1. And so these particles pretty much double almost the count of particles that we had in the standard model. But one of the things that we want to point out is that we've already seen antiparticles. So I wanted to kind of mention this in passing because this is not the same as sort of missing matter or the dark matter. Antiparticles are a part of our lives. We see these in a bunch of different regimes. I've included just a few examples here. So one, cosmic rays. So there are antiparticles, let's say, for example, antiprotons that come in at really high speeds, come in, interact with Earth's atmosphere and result in particle showers that kind of rain down. And this is actually something that becomes an issue when you're trying to do really low energy experiments, because then you start seeing, if it comes in and hits your experiment, then you start seeing interactions of this particle with your experiment, for example. And we can also look at this. This is an example of a detector that's actually on one of the satellites that's orbiting Earth to kind of study cosmic rays. We also see antiparticles, and we use them as tools in particle accelerators. So some of the accelerators that we have will speed up and smash together electrons and positrons to get this really high energy collision, and then see what comes out of that once they've annihilated, and then things start to cool down again, what other new particles are formed. And it's not just in physics that these are used, it's also in other fields like medicine. So people have been studying how one might use antiprotons to target tumors for cancer therapy. And a technique that's used for medical imaging is PET, which is actually positron emission imaging. positron emission tomography, excuse me. And what you're looking for is essentially radioactive decay that's resulting in these emissions of light that come from and positrons. So these are a part of life and we see them frequently. And so we know that it exists. It just doesn't exist in the quantities that we expect. So as I mentioned before, the way that the standard model understands particles interact, if you have an interaction that then where you're forming particles from some, let's say, high energy collision, you would expect matter and antimatter to be formed in equal amounts. So you'd have perhaps an electron and a positron that both come out of this reaction. If this is the case and you have these equal numbers in the early universe when everything is really close together and sort of really dense, what you might expect on average as a whole is for the positrons to see the electrons again, to find each other again, and to reannihilate. And then at that point, you have the emission again of this light, and now you are not looking at matter, you're looking at energy. This is not what we see. We're sitting in chairs, we're eating food, we're living in buildings, and what we see around us on a regular basis is all formed of matter. So up and down quarks, electrons, neutrinos. And the question is, where is all of the antimatter? If what we are experiencing in our location is typical, why is there more matter than antimatter in the universe? So this is one question that we're trying to answer. The way that we're going about it right now, so there's definitely a lot of work going on it from all kinds of directions, but one thing that you can do is sort of take a step back and think about it from a different perspective. And this you can do by kind of asking a slightly different question. So one way you might reframe this question is, well, is there a way to get around the symmetry of producing particles and antiparticles in equal amounts? Or is there some process that perhaps favors one over the other, for example? Or if you have produced them both, what is it? What kinds of processes? Maybe if you haven't, what kinds of processes might actually result in the production of matter without the same amount of antimatter? Well, let's come back to this table. And I would like to point out something that I kind of glossed over the first time, which is that these bottom particles, the neutrinos, actually don't have an electromagnetic charge. And so it could be the case that potentially if the main idea is that you're switching the electromagnetic charge, you're flipping the sign, what if the neutrinos are their own antiparticles? Could this be the case? If it is, then this might give us a hint about a certain way that you could potentially end up with more physics. And an example of that is the following. So we talked a little bit about nuclear decays. There are a few different kinds. I'd like to describe right now this beta decay. And so oftentimes when you have a nucleus, so let's say a collection of these neutrons and protons, it can undergo a transformation to a different kind of nucleus. And so it would, let's say, skip a place or move to a different place on the periodic table of elements that we may remember from chemistry. So let's say there are some cases where you have a nucleus and you have a neutron that emits an electron. Then that neutron now becomes, let's say, a proton. So now your nucleus, you have an extra proton, so it's moved up a space on the periodic table. You have an electron. Well, it turns out to keep some of the laws that are symmetries that we use to describe the ways that these particles interact, it also needs to emit a neutrino. And this is because we're trying to conserve something called lepton number. So we talked a little bit about how quarks were that first group, leptons were that second group. One of the symmetries that we use to kind of describe the specific interactions that tend to happen or that we have tended to see is that similar to how we expect matter and antimatter to be emitted in equal amounts, we also expect in this type of decay, leptons to be, you should have a something with a lepton number of equal to positive and something with a lepton number equal to negative. And so the overall change in the lepton number should be 0 in this case. There are some cases where, because of energy reasons, it just doesn't really become favorable for the atom to sort of change into another atom by emitting just one electron. Instead, that interaction doesn't really happen, but it may be, especially in the case when you have equal numbers of neutrons and protons for various reasons, that you'll have something that emits 2 at the same time. And this is known as double beta decay. So we've seen beta decay and we've seen double beta decay in its normal form, which is 2 neutrino double beta decay, where we have a nucleus that has a couple of protons that emit a couple of electrons and a couple of neutrinos. And this is a really rare process, but it has been measured. This also conserves lepton number symmetry. So we've seen this. If the neutrino is its own antiparticle, it could be that what you end up with is no neutrinos being emitted, because sort of in a nutshell, they kind of annihilate against themselves. Not the best way to describe it, but if the neutrino is its own antiparticle and this happens, then all you would see in the final setup is your new nucleus and 2 electrons. And this is breaking the rule about lepton number symmetry. And it's also resulting, and note that the lepton number symmetry, because what are being emitted, these neutrinos are also technically antineutrinos, so it also helps you keep the matter-antimatter piece correct. What you're now emitting is just electrons, and you have no antineutrinos, the neutrino and the antineutrino being the same thing. And so now you've basically been able to sort of have this symmetry violation, which could potentially tie into ways to generate matter antimatter asymmetry. And this process is known as neutrinoless double beta decay. And so this is what we're looking for. Just for clarity, I think I might have misspoke a little bit in terms of the antimatter part. The main thing is the lepton number symmetry. All right, so as I mentioned, this is sort of just a picture of how this might happen. So we've already described this in some detail, but essentially what we're looking at is sort of a plot of the atomic number versus the nuclear mass. And in this sort of neutrinoless, or in a double beta decay, you would expect the mass number to change by 2 for the proton. So you move over 2 spaces in the periodic table. There are only a handful of elements that can actually do this. And so this table on the upper right lists some of these elements. And it also lists, when you sort of have this element in nature, there are specific isotopes of this element that will work. So you can have different number of neutrons for a given number of protons. When both the number of protons and the number of neutrons is even, then this is a potential candidate for this double beta decay, and potentially for this neutrinoless double beta decay. And it also describes the energies at which you would expect to see this happen. When, let's say, the electrons that get emitted show up in your detector, what range of energy are you expecting to see this sort of register as? And this is important because it kind of then indicates to us which types of materials we might want to use to look for this decay. If it can be in an energy range where we don't expect to see a lot of other things interacting, and if there's enough of it that it's not super expensive or super hard to get enough of this to see enough of these interactions, or to have a large enough detector or see enough of these interactions to actually detect it, since it is supposed to be so rare, then we can start to think about what we want to do in terms of an experiment. So I mentioned this energy. So what you would really expect to see is what you can do. You can build a detector that looks for those 2 electrons that get emitted to sort of interact with the detector. And with a 2 neutrino spectrum are the case where you have 2 electrons and 2 neutrinos that get emitted. what happens is the neutrinos carry away some of the energy, and you don't really see the neutrinos because they interact so rarely with anything it's kind of no telling how much energy they're really carrying away. And so there's sort of this continuum that you get with respect to the energy that the electrons have available to put into your detector. But if it's neutrino-less double beta decay, then what you end up with is all of that energy from this interaction goes into those two electrons, and that's how much you expect to get in your detector. And so that's what you would expect to see it as a much narrower peak and sort of at the end of the spectrum where there's nothing that's being carried away by these neutrinos. And so the relative sizes of these peaks is actually quite exaggerated for effect. This red would be much, much smaller. And so this is the reason why you're trying to do this in a really huge detector so that you can actually build up enough of these events to be able to see this peak formed. All right. So I kind of described the motivation for this, ranging from the fact that we really, really, really want to know how the nucleus works and how the rules for particle physics work. And it has an important implication for how we understand the world that we live in the universe, and will help us to better understand sort of like how we ended up with this imbalance potentially between matter and antimatter that got formed, and potentially could also help us understand better what we're dealing with when we are looking at these particle and nuclear physics interactions. So how are we going to look for this interaction that has so much interesting potential? So there are a lot of different search methods. There are a lot of different experiments. A few examples are kind of illustrated here. One example is these sort of time projection chambers, where you have these huge chambers that are filled with gas, and the particle comes in and creates tracks. There are also scintillators, where maybe your particle comes in and interacts with a particular type of material and emits light that you can detect. And then you also have these cryogenic bolometers, which are what I'm going to focus on. And particularly, I'm going to focus on an experiment that's called CORE, which, as mentioned in the introduction, actually stands for the Cryogenic Underground Observatory for Rare Events. So one of the first things that you want to do is get the material that you are going to be looking for this event in. So in these types of bolometer experiments, and we'll describe how they are designed more fully in a minute, your detector is actually the same thing as your source. So what we do is we find an element that we're interested in studying, and we embed it in this case, crystals, which we are really regular structures in which we're able to kind of carefully control. And we're able to control also the sort of impurities and the extra backgrounds or other elements that get in that might kind of confuse the signal. With crystals, we can kind of try to minimize all of that. So our detectors are actually sort of formed from a couple of different things. One, so the element that we chose to look for this neutrinoless cell beta decay is tellurium. And specifically, we're looking for it in tellurium-130. And so this picture on the upper right kind of shows the crystals that were formed with this. It's actually tellurium dioxide, so TeO2. And then we also instrument them with sensors. And as it turns out, the sensors are also made from crystals, but they're made from semiconductor crystals. And so this is what we use is NTD germanium, which we'll talk about a little bit on the next slide. And then they're also instrumented with heaters, which are formed from silicon. And what these heaters do is they give us a way to kind of carefully inject a known amount of energy into the crystals so that when we can calibrate it, essentially, so that when we're measuring amounts of energy from other particles, we know how much we're getting. And we also know how it changes based on the small changes in the environment that the crystal is sitting in. Now, what about these sensors that I mentioned? Well, these are really interesting because what it is they're germanium crystals that are grown at high purity. So kind of as in the example shown on the upper left here. These get cut down into wafers, as shown here. And then we actually put them in a nuclear reactor. So for example, there's one at MIT where we bombard them with neutrons. And what this does is it causes another radioactive decay in the germanium. and it sort of changes some of the elements in a controlled way so that we are able to get a certain number of what are called dopants, so other types of atoms in there. And this allows us to adjust sort of how these sensors will react when energy is deposited. So then once that's been radio activated or irradiated is the proper term, we take them out. We have to wait 6 months for those to cool down. And then they get chopped, sliced, and diced into much smaller pieces, very carefully, of course. And they also get coated with, let's say, gold electrodes in a process that kind of allows us to, again, carefully control the way that we read out this change that we get when we have energy that gets deposited into the larger crystal. So what is this that I'm referring to? Well, on the left, this is kind of the design of one of these detectors. So I introduced the sort of three pieces of it. So the larger crystal, and this is the TeO2 crystal, serves as an absorber. So if you have something that comes in and hits this crystal, like you see here with this energy release, it's going to raise the temperature of the crystal. And by having that NTD germanium thermistor or that sensor mounted on this crystal, that's going to change the temperature of this too. And it also changes the amount of resistance that you get if you consider this being part of an electric circuit. Now, the whole crystal is sort of lightly connected or weakly connected to a heat bath or a larger means of getting rid of some of the energy. And so what happens is the energy comes in and gets released, heats up the crystal for a little bit, and then it's able to kind of like ooze out. And so what this looks like for us is kind of like a spike in the voltage that we read out through this thermistor. So what do these look like? Well, we have these crystals instrumented. You can see here the larger pale crystal, like as illustrated on the left-hand side. You've got this germanium NTD sort of instrumented up here. And then the silicon heaters aren't shown in sort of this model that I have on the left, but again, they're used to inject a known amount of energy. So it could correspond to this sort of energy release here. If we want to sort of have a measure of how much the crystal responds to a given amount of energy, and you see that here, and they all get mounted together in a frame. These Teflon supports, which are labeled PTFE here, serve as this sort of thermal coupling to the copper frame, which is going to be super cold, and so the temperature of the surroundings, which we keep on the order of about 10 millikelvin. So that's 10,000ths of 1 degree above absolute zero. The other thing that you see here is sort of how you read it out. So these really small sensors actually have really thin gold wires that then connect them to a more robust set of wires, and we have those covered up. And then that all gets read out further down the chain of the experiment. So that kind of gives you a close-up. Now, when you're looking for these really rare events, you can wait a really long time, and you can also try to increase the opportunities for the event to happen by also building up a lot of mass. And so we try to optimize between both. We look for as long as we can, but we also build large detectors. And in this case, we built a large detector by combining a bunch of crystals. So what you see here is the assembled Poirot detector. There are 988 crystals in this array, and they're assembled into 19 towers. Each tower has 4 crystals on 13 floors, and they're all mounted into this, what you see here, so the bottom of an instrument that's called a dilution refrigerator. Now, this is, now having the detector here is sort of like the interior part of this structure. So there are a few things that I would like to note about what goes on when we're dealing with this. And one is that if we're trying to measure such a sensitive signal, you might wonder how we try to protect it from other things that would either be so large that it will sort of wash out the signal, or it might kind of look like what we're looking for, but not actually be the right thing. And so one of the ways is, as we mentioned earlier, by just sort of trying to grow these really pure, clean crystals. And once they're grown, following careful handling procedures to avoid them getting contaminated later. Another thing that we do is we surround them with lead, and this helps protect from some other backgrounds. One of the interesting things about the lead for our detector is that it's actually ancient Roman lead. And the reason for this is that typically it's been underwater for a couple of thousand years and hasn't been subject to things like cosmic rays or other potential means of irradiation, fallout from the atmosphere, whatnot. And so it's also not going to be as radioactive, and it won't emit its own things onto the crystals as we're trying to protect it from other things. So you've got it surrounded by Roman lead on some sides. We also have modern lead in places that are a little bit further away from the crystals. Still helps protect them, but we just keep that a little bit further away. And then with this dilution refrigerator, you see that the crystals are on the very bottom stage. The way that this works, you kind of go up through different temperature stages. So we have the dilution refrigerator is actually a combination of a couple of different technologies. One is a pulse tube refrigerator, which uses sort of like the compression and the expansion of helium to cool things down, to remove energy from a system. And so this gets us on the order of 4 Kelvin. And then we also have this dilution unit, which also, again, uses helium, but it uses it in a different way. And what it does is essentially by the time you get to about 4 Kelvin, there are 2 kinds of helium as well. One of them has 2 protons and 2 neutrons, and one of them has 2 protons and 1 neutron. And the one that only has 1 neutron is a little bit lighter than the other and has slightly different behaviors. So they separate when you're at these cold temperatures. Well, if you have them in a container together and you pump on one side of the container, you kind of pull the lighter one through the heavier one. And this sort of makes it go through the surface. And this sort of breaking of this across the surface also is a means of removing energy from the system. And so this is kind of what lets us drop down that last couple of degrees to this millikelvin range that we're operating at. But in order to sort of isolate your system from the rest of the world and maintain that cold temperature, you have to have several layers. And so that's what you see here with these various copper cans. They're sort of thermalized to different temperature stages as you get to colder and colder temperatures. Well, if that wasn't interesting enough, and if it wasn't already a lot of infrastructure, now we have the Correa detector getting, and we see sort of like how it's actually mounted. So another thing that could cause us some issues in terms of extra energy in the detectors is vibrations. So one of the things that's done is the whole cryostat is suspended from what we call a Y-beam on this structure that kind of lets it hang in the air and tries to minimize the number of vibrations that get transferred to the cryostat and ultimately to the crystals from the rest of the environment. And so while you don't see it here, this is actually about 2 stories tall. There's a floor sort of at the bottom of this red structure. You can see the main support plate that supports that Y-beam, and there's vibrational isolation. And then you see the concrete beams and the sand-filled columns. And this, on the bottom here, this additional shielding. So we also have lead shielding on the outside of the cryostat, and we have this polyethylene shielding to help get rid of neutrons. This gets raised up around the cryostat when we're ready to operate. And there's sort of like a bottom laboratory down here where you can access the rest of this when you're not working on the cryostat itself. And so the area that we're in also has a lot of seismic activity, roughly speaking, in general, as much of the world does. And so there's also seismic isolation. Now, speaking of the area where it is, another means of protecting the experiment from these extra backgrounds is to have it underground. And so we do. So this isn't showing you the underground lab, but it is showing you the surface laboratories of Grand Sassanil National Laboratories where the experiment's actually held. And the laboratory where the detector is actually underneath this huge mountain. And that actually helps protect us from some of these cosmic rays that we discussed earlier. So the mountain acts as an overburden with a few thousand meters water equivalent of sort of protection, where these cosmic rays can kind of lose all their energy and interact before they get to our detector. And that also helps provide the shielding that we need in order to get to these really low, really small measurements that we're trying to make. Okay, well, let me see. All right, so we've talked about the detector, we've talked about the design of the detector and some of the cool things that have gone into it, a little bit of the way that the sensors work. So now what we're thinking about is how we are actually going to look for the neutrinolithic beta decay signal. So again, you have this detector, you have something that comes in, another particle, a photon, releases energy in the detector. And I alluded earlier to the fact that what we're trying to read out is this voltage, we get a pulse. So this is what that looks like on the upper left-hand side here. So this is over a period of about 10 seconds. And so you kind of see, we may start out with the detector nice and cool, and sort of just reading out at this particular given amount of baseline of its original. Something comes in and deposits energy, that's going to raise the whole temperature of the detector, and it also changes the resistance of that germanium thermistor, or that germanium sensor that we spoke of. And when you raise that resistance, and that means that we're now looking at a change in the voltage that we're reading out across the detector. So when the energy gets deposited, that changes pretty quickly. And then when it's losing the energy, you can kind of see the voltage falling. And that takes a little bit of time because of the fact that it's weakly coupled to the heat back through that Teflon that we saw. And so this is the shape of the pulse that we expect to see. Now, what we notice is that this change in temperature, the change in voltage that we have, is going to be related directly to the amount of energy that gets deposited. And so ultimately what we're trying to do is we're trying to count these pulses and find out what the energies are for them, and then we just bin them. And so a pulse of a given height goes into a particular energy bin, and with this we kind of build up a spectrum. Now, we started taking data with these detectors in early 2017, and we've pretty much been continuously operating with a couple of maintenance and operation stops since then. And so we've built up over the last few years a lot of collections of pulses. We also take some time to do some calibration of the detectors, so that we make sure that we understand how the detector is behaving and that things are still working the way that we expect it to. But overall, we at this point have collected almost 2 ton years of data. And so this isn't looking at all of those, but this isn't looking at all of those. What the plot on the bottom kind of illustrates is sort of what we got from the first 10 year, and looking at all of those pulses and kind of understanding sort of what the distribution is as a function of energy. And so you see here that we do have, of course, and as to be expected, an interesting shape and lots of peaks, and we understand where these come from. And so this is the result of simulations, of understanding backgrounds that we do have. We just can't get rid of everything, so we carefully study what there is and try to account for that in the process of the analysis. And so we select events that meet the certain criteria that we expect to be met by events that would be neutrinoless beta decay events. And these include things like, because this is such a rare happening, we shouldn't have a bunch of energy showing up on multiple detectors or multiple crystals in the detector at the same time. So we get rid of events like that. Or if, 2 events happen really close together, it makes it difficult to measure the energy. So we'll get rid of events like that. So we go through and do these careful analysis cuts. And then at the end, what we are left with are spectra that look kind of like the lightest green version that you see here in this plot. And then we hone in on this region that's around the Q beta beta, or the energy where we would expect the electrons from the neutrino stellar decay of our specific isotope, tellurium-130, to be. And we look at how wide that peak is. We account for, again, the backgrounds we expect to be in the area. So there's another product, let's say from the radioactive decay of cobalt-60 that we have to account for, so move that out of the way. But what we look for is an extra peak at the energy that we expect that would correspond to neutrino stellar decay. And as you can see in our case, from the sort of insert in this bottom plot, we don't actually see that extra peak. So what does this mean? And let me make sure that I am good. Okay, so what does that mean? Well, there are a couple of things that we do, but what I'd like to focus on is, well, I'll briefly describe what's going on here. So we do a couple of things. Like we carefully understand how each one of the detectors behaves. So let's say in the upper left corner, we try to see how far down in energy the bolometers are actually sensitive to, and we kind of, or we'll actually go off, and then we'll also try to set a limit on how well our analysis is able to do at a certain energy. And so that's sort of what you see in this upper left corner. We also do a lot of studies where we try to simulate, for given values, what kind of a signal would we expect to see with neutrino stellar decay, and the value that we measure, where does that fall sort of in the spread of those values? And so if we measured something that's really weird based on our detector parameters, then we would want to take a second look. We also want to understand how confident we are in the number that we measure. And we also kind of want to see, we kind of want to understand how well we have fit the peak that we describe here. So all of these things go into evaluating the robustness of our result. And so when we do this, what we're able to do is kind of set a limit on how long the half-life of the decay of neutrino stellar decay is based on our experiment. And so at the end of the day, what we ended up with in this case, as an example, is that we are looking at something on the order of about 2.2 times 10 to the 24 years. And what this kind of means is that we would have to wait that long before half of the atoms in our detector decayed through neutrino stellar decay. Now, for context, this is way longer than, let's say, the age of the universe. And so one way that you can think about it is that so far we're stable. What we understand is that the element that we're looking at is pretty stable against neutrino stellar decay. And so we don't really have evidence that neutrino is its own antiparticle at this point. And so that's something to kind of take into consideration as we try to understand this. On the other hand, we are still looking, and it may be that we see this peak in a future experiment. And so we are actually in the process of continuing R&D or research and development for improving our detectors and continuing to run the detector that we have now. And so this particular experiment also doesn't necessarily account for all the other processes that could happen. You don't have to go straight from let's say the very basic version of neutrino stellar decay to the basic energy of another element. You could have different states that you end up in before you sort of end up in the final state. And so there are other analyses that look at this as well. And so we are still searching for this and still searching for some of the other mysteries of the universe for sure. The detectors that we have are actually really interesting because of the way that they're designed. They're sensitive to other searches as well. And we won't go into those right now, but what I would like to say is that it's just been a really interesting process to look for. And it has a lot of potential implications, both for the way that we understand sort of like the nucleus and the constituents of the nucleus and the way that we understand sort of how the world around us is developed. And so with that, I'd like to say thank you so much for your attention, and it's been a pleasure.